So, I'm not professionally, by the way. My name is Adi, and I was a professionally speak student. I graduated in 2003, but because he traveled out of the country, so he asked me to come and take over the class for him. So I'll be teaching that class for today and tomorrow. Okay? And for the introduction part, actually, for this course, chapter 1, when Professor Lee comes back, he will give you a much detailed introduction about the course and also the scoring, the assignments, and everything related to the class. So on my part, I'll start from chapter 2, and then when he comes back, he will take you back to chapter 1 to give you a much more detailed and proper introduction to the course. Okay? So once again, welcome everyone, and good to see you all. So this class is titled Foundation Engineering. I believe everyone here has taken soil mechanics before, right? So if you have a good understanding of soil mechanics, then foundation engineering should not be very, very complicated for you, because most of the principles in foundation engineering are all based on what you learn from soil mechanics. It's just you are transposing the idea, like the theoretical concept, to the application in the field. Okay, try to build structures. Is everyone in this class is from Paraguay, or you have students from what? What's you?
I'm from Belize.
Oh, Belize, no. Good. Anyone from Indonesia? You are. Okay. So, do you guys know Dr. Jora? Or was he your teacher in Paraguay? No? Or, I think he went last year, so maybe you guys, he didn't teach you guys. Okay, so when we talk about foundation engineering, I think the first question we need to ask ourselves is that what is foundation engineering, or why do we even need to consider foundations? If we are engineers, particularly like civil engineers, most of the time what we do, we build structures, right? If you build a structure, you have to make sure that it is safe and stable. So the foundation is like the bedrock of your structure. If your foundation is not good, then nothing happens, nothing works. So we want to make sure that our foundation is not only safe, but also even the deformation or the settlement that it undergoes is adequate or is satisfactory. So that's why foundation engineering is like so important. Whatever we do, whatever we build, needs to be built on a strong foundation. Okay? So, but in order to build a foundation, we have to consider several things. For example, if we are going to design our foundation, we need to know the soil properties. Is the soil weak? Is it strong? Is it a good soil? Is it bad? How do we determine that? It's all from the soil properties, right? How you design the foundation depends on the properties of your soil. Like the way you design the foundation here, and the way you design it over there, and the way you design it over there should be totally different depending on what the soil properties at your site. Okay, so on the one it says, if we are going to consider like the design parameters for soil, what do we do? The first one is the soil strength parameters. It determines how the strength of the soil, okay, how strong or weak the soil is, whether it can bear the structure. So this part we may consider two things. We have the drain analysis and the undrained analysis. And when we talk about drain analysis, the concept is actually very, very simple. It usually happens in sandy soils or the soils that have coarse grain. Why? If there is water present and then you apply loading on this type of soil, what happens? The water will come out. If you remove the loading, what happens? The water goes back in. So that means the pore space is large enough for water to easily go in and out of the soil. So we call that the drain analysis. And in this condition, the strength of the soil is determined by what? The internal friction between the soil particles. That is the frictional force between the particles. So when we are doing the drain analysis, we consider the effective friction angle. Okay, that's what determines the strength of the soil. And for on-drain analysis, we are talking about, let's say, clay or silt. They are very fine. Okay, even if water is present in clay, if you step on it or you put a loading on it, it doesn't mean the water will immediately come out. Or when you remove the loading, the water will immediately go back in. No, because the permeability is very, 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 very small. So in that case, we say is on drain. That means water cannot easily go in or out of the soil. And in that case, the strength of the soil is determined by the on drain shear strength. So the two scenarios are different. It's like when you're having a problem, the first thing you even consider, oh, is it a drain problem or is it an on drain problem? Then you know, okay, will the strength be controlled by the effective frictional angle or will it be controlled by the shear strength? Okay, and this one is the strength parameter. Another very important parameter is the compressibility. Why is this important? We want to make sure that when we build a building or we have a foundation, the settlement is reasonable. Okay? For example, you build a foundation and it didn't fail, it's still standing there, but you have a settlement of about 10 centimeters or 20 centimeters. The building keeps going down. Like, that's not reasonable. Maybe the first floor will come to B1. Okay, so that's also not reasonable. So why do we need, that's why we need this soil compressibility parameter. It tells us how much the soil compresses. Okay, so in this case, for the drain analysis, we might consider the Young's modulus, right? Which is the ratio of the stress to the strain, or the compression index. When we talk about soil materials, the compression index is when you apply loading on the soil, the rate at which it compresses. Okay, if you apply a loading, what will happen? It will definitely compress, it will go down. And the swelling index is when you remove the loading, what happens? It will try to rebound. Okay? It will not go back to exactly the same volume, but it will still swell up a little bit. So this is called the swelling index, and this is the compression index. Okay, so these parameters are also very important when we consider the compressibility of the soil. And then we have the on-drain. In the on-drain case, for example, in clay and silt, we will consider the on-drain Young's modulus, okay? Because those ones are not significantly affected by its CC and the CS. And another important factor that we might consider when we are dealing with foundation engineering the soil properties is the at-rest lateral earth pressure coefficient, okay? A0. Because typically when we calculate the sigma, we will calculate the what? The vertical component, okay? So we might need the lateral earth pressure coefficient to convert this vertical force into a lateral force, okay? Because if this is our foundation, we build it like this, and then we know the vertical force here, we know the value, but that's not the most important thing. What we want to know is, what is the horizontal force that is acting on a foundation during this soil? So that's why this parameter is also important. Okay, so here we have the soil strength parameters, and this is the Moore-Coulomb failure criterion. I think everyone here should be familiar with the Moore-Coulomb failure criterion, right? Should be quite straightforward. So it's based on the fact that the shear strength should be equal to cohesion plus stress multiplied by the angle phi, right? But if we are going to do the drain analysis, okay, the water can easily go in and out, or coarse grained soils, sandy soils. typically the C prime is 0. They don't have much cohesion between the particles. So for that case, the CR strength becomes, okay. So in this case, if you are going to draw the Mohr circle, it's going to be most likely something like this. You might have these, and then these, and then something like this. Okay, so this might be your sigma 3, sigma 1, and then you have the same thing, sigma 3, sigma 1. Okay, so that's the case when we are dealing with the on-drain. And this volume here is the frictional angle. So in this case, the CR strength of the soil typically depends on the friction angle. Okay? Contrarily, if we are doing the on-drain analysis, the friction angle, because the strength of the soil in this case does not depend on the friction angle. Okay? That is the on-drain analysis. So for that, this is 0. So if the friction angle is 0, and in that case the C is equal to the SU, that is the on-drain CR strength. So here, the on-drain CR strength, this value is just equal to SU of the soil. So you will realize that for the drain analysis, we will have something like this. If we draw the Mohr cycle, you have sigma 3 increases, you can increase the sigma 1. So, okay. Okay, so this is the basic explanation for the sigma 3 and the sigma 1. The sigma 3 is the what? The confining pressure, okay? You confine the soil, you hold it in there. And the sigma 1 is the loading you apply on the soil, okay? So typically it is larger. So if you increase this value, sigma 3, then the value at which the soil will fail for sigma 1 will what? It will keep increasing, right? So that's why once you increase the sigma 3, the sigma 1 keeps increasing, and the Mohr circle will get bigger and bigger. Okay? This is the case when we are working with the drain. Okay? The water can easily go in and out. But if it is the on-drain, in this case, the failure criterion for the Mohr Coulomb failure criterion, it does not depend on this, the friction angle. So you will realize that if you draw your Mohr cycle, typically it's just like this. You will have something like this. Okay, maybe this is your failure criterion. Okay, so they will have the same size. So this could be your sigma 3, this is your sigma 1. Okay, you increase sigma 3, sigma 1 will also increase. Just like that. It doesn't change. Because it only depends on the SU value, not the friction angle. Okay, and here we have a simple diagram trying to explain how we can determine the effective friction angle for dense and loose sands. Okay, so the behavior for dense sand and loose sand is typically quite different. For loose sand, if you apply, okay, this one sigma 1 minus sigma 3 is called the deviator stress. That is the stress difference between the confining pressure and the sigma 1 that you apply to it. Okay, this is the deviator stress, sigma 1 minus sigma 3. If it is loose, what happens? You apply loading, there will be strain. Strain is what? Deformation, right? The soil will deform. If you apply loading or stress to the soil or loading, what happens? It deforms. So it will deform until it reaches what? The ultimate strength. The ultimate strength means what? The strength at which the soil will fail. Okay, so the behavior is just like this. It's loose, so it goes up all the way here. It reaches the ultimate strength, and it fails. But if the soil is dense or highly overconsolidated, that is highly compacted, what happens? You can see that the deformation. Look at here. We may have the same deformation here, but the load needed here is much higher, right, compared to the loose sand. But what you observe here is when you reach the peak, it just doesn't go like this. It goes up and comes down, which is quite interesting. Because this dense soil is already stronger than a loose soil, right? So if you apply loading onto it, what happens? The deformation will not be that much compared to the loose one. But it will go up to a peak strength. The peak strength is like we will experience a very large deformation. The deformation will become much bigger. That is, it is approaching failure. It reaches this point and then it comes down. Why? It's like if the dense soil reaches this point, the soil particles will kind of break a little bit and then they will rearrange themselves. So that's why this comes down here. Okay, so typically in design, we will most of the time focus on the ultimate strength. Okay, so here we can see some range given. Okay, so if we are dealing with the soil material like sand, round, grain, uniform, the loose material, the effective friction angle is actually smaller than the dense material, and it's quite reasonable. If you think about it, if they are not tightly packed together, then the force of attraction or the internal friction between them should be smaller, right? And if they are more tightly packed together, then the internal friction should be high, right? So you can see like sandy gravel, silty sand, inorganic silt. Okay, so typically like the more coarse grain the material is, also the higher the friction angle. So you can see the for sand and gravel, whatever, typically the effective friction angle will be larger than the fine grained material like inorganic silt or silty sand. Okay, so this one also gives us some representation where we can just use the dry unit weight to estimate the friction angle. But typically, as an undergraduate student, most of the problems you will deal with, you will be given something like this. Okay? You will be given something like this. And then you can sometimes use your own judgment to determine what is the effective friction angle, whether for loose or dense materials. Okay, and here is estimation of effective friction angle. How do we determine this parameter? We need to do some sort of a test, a field test, okay? So this is called the SPTN value, that is the standard penetration test. They will have a hammer, drop it. So usually it's the hammer is dropped in two parts, okay? Have anyone seen the SPTN test before in the field? No? Okay. So typically what they do is like there will be a truck or a car and it will carry a hammer or a weight up to a certain height and then it drops it. And then the same, it goes up and then drops it. So the first 150 millimeters is not considered. It's like the preliminary stage. And then the second 300 millimeters will be considered. So the end value for a soil here is the amount of times that you need to drop the hammer for it to complete this 300. In some soils, maybe this end will be 10. In some, maybe it's 20. In some, maybe it's even more than 50. Okay? So the stronger the soil, the higher this value will be. Okay? And the higher this value is, that means the more dense the soil is. The more dense the soil is, that means what? The friction angle will be larger. Okay? Larger friction angle. So you can see here the estimation based on the SPDN value, but there are also so many factors that actually affect this end value. Okay, this is the end value when we drop that hammer from the car or the truck. This is the end value you get. But based on experience and engineering judgment, it is believed that some of the energy from the hammer is lost. Okay, so for example, the energy ratio, depending on the type of hammer, like this is Japan donut hammer, the energy ratio, the value is CERP is 1.3. And for some hammers, the energy ratio is only about 0.8. So what does it mean? You drop the hammer, but not all of the energy is actually transferred to the soil. Some of it is lost. Okay, so they account for that here. And the borehole diameter, the diameter of the borehole can also have an influence on the end value. So is the sampling method. What type of sampling method are you using? Okay, so that one also is a factor here. And then the rod length, that's the length of the rod that you're using. So all these factors affect the end value, the actual end value of the soil. So it is called N60. Why is it called 60? Because it is believed that only 60% of the energy that is from the hammer is actually transferred to the soil. Okay? The rest of the energy is probably lost along the way. So that's why we will get this N60. Once you get the N60, it would have been great if we could just stop here and use it. But in some instances, you still have to find the N160. Okay, so this one you just normalize for the overboarding pressure. Okay, you normalize the N60 for the overboarding pressure. In this case, the overboarding pressure is just the atmospheric pressure divided by the vertical stress. Okay, so once you normalize this, you can get what is called the N160. That is the corrected SPDN value. So based on this, let's say if we get this value is 50, we come here. Oh, okay, maybe we assume it's here, then we can know what's the friction angle of the soil we are dealing with. If it is 10, you just come here. So here we can see we have two different lines. Which one do we use? This one was a research done in 1996. This one also was the suggestion given in 2004. So this is actually you do multiple tests in the field. Okay, if the SPDN value is this, what is the actual value of the effective friction angle? And once that is obtained, what do? They draw a line of best fit. Okay, you try to draw a line of best fit. So this one, Adanaka was this way. His suggestion was this, and Chen et al. Came up with this suggestion. Okay, so you can see you can use either one, I believe, but if you want to be more conservative, then maybe you will go with this, right? But if you don't want to be too conservative with your design, then you can check this, because you can see from here, when it's 50, it will tell you, oh, the effective friction angle is almost like 46. But in this case, it's only maybe 43. So this actually, the difference between 43 and 46 will have a huge impact when you design your foundation. Okay, because these values affect the strength of your soil. Okay, so when we use empirical calculation, sometimes we can have a fixed value. Okay, x equal to 2, we know it. But most of the time, when we deal with soil, most of the things are not really fixed. Okay, you will need to use a lot of your own judgment to make the decision. Okay, so apart from the SPTN, another technique that is used to determine the effective friction angle is the CVT. Okay, I think if you haven't seen the SPTN, it will be quite hard to see the CVT. Has anyone used it before CVT? No? Yeah, because it's a lot more expensive, so and a lot more rarely used. So usually the SPTN is used in the maybe coarse soils or maybe like gravelly materials. But when we're dealing with soft soils, then we can use the CPT, the cone penetration test. You have some sort of like a cylindrical cone, it's like a cylinder. And then the tip It's like a cone. And what do? They drive the cylindrical cone into the soil, okay? But when you are pushing that cone into the soil, there will be some sort of resistance. And that resistance is called QT. Okay, why is that resistance important? If your soil material is very strong and you try to drive something in the soil, the resistance will be what? Smaller or higher? Should be higher, right? But if the material is weak or softer, if you try to drive it in, what happens? The resistance should be smaller. Okay? So based on that, we can use this equation. Okay, by the time we drive it in the soil, we will get QT. That is the cone resistance. Then we know this, we can easily calculate that. I think by now everyone knows how to calculate this. And then this one is the atmospheric pressure. Okay, you can get this value. And once we get this value, we can find the approximate effective friction angle, okay, based on the cone penetration test. So you can see here, this is also so many experimental results right here. So that's why here they say what? Approximately. Because you do so many experiments and then you draw the line of what? Best fit. Okay? Okay, so yes.
For example, in the SDT value, how do you know which method to use? Sand or
So usually when you know that the soil condition at the site is probably clay or silty soil, you can typically use the CPT. It's more accurate, but if it is coarse, like sandy material, like which is more coarse, then you can use the SPDF. But in a lot of cases, a lot of people also don't want to use the CPT because it's also more expensive. So even though if you use it in silty material or clay material, the result is not as accurate as the CPT. Some people might still want to use the SPT and because it's cheaper. But when your soil material is really too hard or too strong, then you cannot use the CPT because the tip of the cone cannot penetrate into the soil. Or every time you might need to change it, which is very expensive. Okay, so if no problem with the effective friction angle, then we can proceed to the undrained shear strength. Okay, so for the undrained analysis, we typically focus on what? The undrained shear strength, that is the SU. Okay, for the drain analysis, we focus on the effective friction angle. For the undrained, we focus on what? The undrained shear strength. It is what controls the strength of the soil. Okay, so here we have two different graphs. Okay, this one is what called remolded clay, and this one is the undisturbed. Okay, so what does it mean undisturbed, and what does it mean remolded? Okay, so when we talk about undisturbed clay, that means clay in its natural form. Okay, it did not change. Nothing changes with the, let's say, the mechanical properties or the physical properties. It's in its natural state. But the remolded clay, that means the structure of the material has been changed. This could be due to loading. Sometimes when you are doing construction or you are doing excavation, okay, these undrained materials like clay, the structure will change. So that actually affects what? The strength of clay. So if you think about it, if this is your clay material and then you remold it, most of the time when you remold clay, what happens? The plasticity of the clay increases. If the plasticity increases, what happens? That means it will be easier for the clay to deform. Okay, so that's why here, when you just apply this amount of stress, you can see it's not that much, but the axial strain is almost this, right? But for the undisturbed that has not been changed, what happens? You need much larger stress to have the same amount of deformation. Okay, but why do we suddenly have this drop? Because when you apply a load into a certain point, you begin to affect the structure, the physical and the mechanical properties of the clay. So it will also experience a similar thing, right? It will drop significantly after some time because you already disturbed. But in general, the strength of the undisturbed or natural clay is typically much higher than when it is remolded. But typically when we are doing construction, we might be dealing with remolded clay. It's not like you remold it one by one, but it's like when you are doing excavation, you have a lot of heavy equipment on the side. So that will disturb the physical and the mechanical properties of clay. So it's no longer undisturbed. It will be classified as remolded clay. Okay, so we can use that to determine the undrained shear strength. So here you can see it's the same thing. A lot of experiments conducted. Okay, if this is the liquid index, what is the remolded undrained shear strength of clay? And based on this, we have this equation. Okay, SU of remolded clay over this PA, which is the atmospheric pressure, should be equal to this. That is the multiplied by the liquid index. Okay, so all these are based on experimental data. Okay, so if it is remolded clay, we use the other equation, and if it is OCR clay, this is the equation. Is anyone familiar with what OCR clay means? Yes, over consolidated. Okay, so let's say this is our clay. Maybe before it has been subjected to something like this. Something like this amount of loading, okay? But that is in the past, let's say maybe 20 years ago, 30 years ago, 50 years ago, 100 years ago, whatever. But recently, at this present moment, it is only subjected to 5,000. So we can say it is what? Over consolidated. It has experienced a larger load in the past than what is presently on it. Okay, so that's what over consolidated means. The loading it experienced in the past is much larger than its present condition. And typically for clay, it gets stronger if it is over consolidated. Okay? The larger the, you can actually see it here, it's raised to this power, right? So if it is 1, okay, this will increase, but if it is 2, it will increase even more. If it is 3, it will increase even more. So the larger the OCR, the stronger the clay will be in this case. If it is OCR clay. Okay, and here they give us more like estimation or more techniques that can be used to determine the undrained shear strength of clay. So this is the vein shear test. So it's another type of equipment different from the CBD and the SPG that can also be used to determine the undrained shear strength of clay. Okay, this one also is a suggestion. This one is the CPT result, but Westray and Uvar. So they came up with this estimation. So you can also use this equation where the QT is the cone resistance for the CPT, and this is the vertical stress or the overbody pressure, and divided by 16. Okay, so there are so many techniques and tools that can be used to determine the strength of certain materials. Okay, so if you have so many techniques and tools, how do you determine which one do I use? Right? You might think, I have so many choices, which one do I use? I think the number one problem is if you don't have to worry about money, then you can think, okay, which one is most ideal for my soil condition? So first you need to understand what type of soil condition are you dealing with. Okay? Like different techniques might be more suitable for different soil conditions. Like if you are dealing with gravelly material or the soil that is very, very strong, it might not be ideal to use the cone penetration test. You can say, okay, I will use the SPT and test. But in the real world, sometimes also it depends more on the money, the cost. Okay. Okay, so we talked about like the different techniques we can use to determine the on-grain shear strength. And the next one is the Young's modulus. Okay, this one is typically used to give us an idea to the deformation. Okay, the rate of deformation of the soil. Okay, so we can see here the deviator stress, that is the sigma 1 minus the sigma 3, and then the axial strain, that is the deformation that we will experience. Okay, so I think we can all remember that Young's modulus will be stress over strain, right? Stress over strain will give us the Young's modulus. Okay, but this, most of the time when we are dealing with soil, it's not linear, it's non-linear. So it's not just like this. We might have something like this. Okay, it goes like this, it goes like this. It's not really a linear material. So to determine the Young's modulus, you can determine it in different ways. For example, this EI means what? The initial Young's modulus. You can use this in situations when you experience what? Very, very small strain. That is, the deformation experience is very, very small. Then you can use the initial EI. Then we also have the secant modulus. Okay, so this one is from the starting point to a certain point. That is, it can be based on your own judgment. Okay, for example, if I have something like this, this is my stress, this is my strain, and it goes like this. Okay, if I want to determine my Young's modulus, I can say I will, from here, this is my initial phase. Okay, maybe I will see maybe almost about 50-60% here. Then I draw a line from here to here. Okay, I say this will be my Young's modulus. Okay, it's like an average. It gives you an average, an estimate, which is different from this one. The EI is just here, just the initial. Okay, this one gives you an average. So when we are dealing with large cases, bigger problems, then we might use the secant modulus. You also see another one, this one here, ET. The T means tangent, tangential Young's modulus. This, you want to determine the deformation at a specific loading condition. Okay, if my load is at, let's say, 500, I want to know what is the deformation. Then I will draw the tangential Young's modulus to determine that. Okay, so sometimes when do we use this? You might want to consider when your soil is like this, the beginning is linear, then it reaches the plastic state. Okay, the deformation becomes larger. So you want to find what is the Young's modulus at that point. You can use the tangential Young's modulus. You just draw a line on the cover there. Okay, so I will just come here and then say, let me find what is the Young's modulus at this specific point. It's more like local, it's not general. Okay, so the EI is just initially. The ES, the secant, it gives you an average. Okay, and the tangential gives you the Young's modulus at a specific point, okay, or a specific loading condition. Okay, so we also have portion ratio. It's also another thing that affects the deformation or the deformation characteristics of soil. Okay, so portion ratio actually measures what? You can say mil. That is the transverse deformation with respect to the longitudinal deformation. What does it mean? If I have something like this, right? Oh, I'm so bad at drawing. If I have something like this and I apply loading onto it, what will happen? It will deform, right? It will change shape. So, okay, let's assume that the loading is from both ends. It will change shape. If this compresses, what will happen here? Where does this material need to go? They need to go somewhere. So they might come out here, right? So the ratio of this to this is the Young's modulus. Okay, and if you think about it, typically when the material is loose, this is smaller. Why? Because if the material is loose and then you push it down, there is still space for it. It first will occupy the space here before it will go outside. Right, because it's easier to go down than to spread to the side. So it will first come down here, then push out. But if the material is loose, you push it down, most of it will just move in between the spaces, right? Before they start moving laterally. But if the material is dense, it's very, very dense. Okay, let's say this material is super dense. If I push this, there's no space for it to go down. Where will it go? It has to push it outside. Okay, so that's why you will realize that the Poisson ratio for dense materials is typically higher than the loose materials. Okay, it's just based on that concept. You push it, it has space to go in. Okay, most of it will just stay in the transverse direction. But if there's no space for it to go, where will it go? It has to go into the longitudinal direction. Okay. Okay, so here we also have the typical range for the Young's modulus. For loose soil is typically 100 to 200, and here is the atmospheric pressure. Okay, just remember that. And the medium materials is 200 to 500, and for dense is 500 to 1,000. So the more dense your material, the larger the Young's modulus will be. Okay, so if you are working with loose sand and dense sand, and then you do your analysis and then you find out that the Young's modulus for the loose sand is higher than the dense sand, then you probably did something wrong. Okay, you have to go back and find out where or how you made that mistake. Okay, so those are some of the things that you can already have like in mind. And here we have a similar thing. We can also use the SPTN. So you can see the SPTN was not only used to determine the internal friction angle, but it can also be used to determine the Young's modulus. Okay, so like most of these tests, you can do one test, but you can use that one test to find so many different soil parameters. Okay, and then here we have the drain condition to determine the Young's modulus when we use the CPT, that is the cone penetration test. Okay, so you can see this is the equation. We have the tip resistance, the overboarding pressure, we get this value, then we substitute this here. This is the Poisson ratio, and then we can estimate the Young's modulus. So you can see like there are so many different alternative ways to solve for the same thing. How do you determine which one to use? It's the same principle. You go back and see what is the condition or the state of your soil. Then you choose which technique or method to use. Okay, so here is the same thing. We can also see the range, soft, medium, steel, okay, for the Young's modulus. That's the incline. So the more dense, the higher the Young's modulus will be. It's the same here. Okay, and here we also have some figures that gives us equations that we can use to determine the CC, that is the compression index, and the CUR, that is the on-load-reload index. Okay, when you unload and then you reload. Okay, when we deal with soil, if you compress and you remove the loading, then you load it again, the behavior is different. It will not behave the same. Okay, because you are doing some sort of changes to the physical or the mechanical properties of the soil. The shape will change, the structure will change. Okay, so we also have this called the on-load reload index, depending on the loading and the unloading. So here you can see all these are experimentations that we have performed by people, and then they gave suggestions based on the plasticity index to find the CU and the CUR. Okay, I think we can stop here for today. See you guys tomorrow. Have a nice day.